This is
No.
session, so why?
No, it's not.
What if folks
do come in? You never know.
All right.
Okay. Welcome to our Lindiff review. Last night we talked about a lot about first order and second order differential equations. Today we're going to focus a lot on matrices. What we kind of learned about in this class is the relationship between linear systems of equations, right? That's our kind of our ballpark when it comes to using these matrices and having this kind of math we analyze. So you'll notice that we have when it comes to dimensions for matrices, actually one big thing that actually kind of is was kind of slipped me up for a little bit was understanding the rows and column relationship between within the matrix. So right here, of course, these are your, let's see, to figure out. Oh, there we go. Is it writing now? Yeah. So right here are your, huh? Yeah, is that color good for you?
Yeah,
Guess we.
you're chilling.
That's our row, and of course that's our column. So this is a 3 by 2 matrix here. Okay, an example of that. Um, so if we go, within this matrix world, we can do different kinds of math, right? We can add, we can subtract, and whenever that comes up, adding and subtracting, we have to make sure the both matrices are both the same dimensions, right? Of course, for adding and subtracting, that's basic. But for this class, you don't really focus a ton on that. Mostly you focus on multiplying matrices, right? So there's a few ways that you can go about multiplying matrices together. We can do this row of A times column B, well, that's going to be the dot product. So you have this A times E, and it'll be B times G right here. That's your first element. And it'll rinse and repeat, kind of be this A times B, no, A times F plus B times H. That's your second element here, and so on and so forth. Other applications you can also do matrix vector multiplications where you have your whole matrix here times by this vector, which is just that column right there. And then same thing, matrix multiplied by this column, this FH. Row of A times row B. Actually, row of A times B. So you'd have your row A, kind of similar to 2, but you just have your row instead. So AB times by the matrix EFGH. And you have your columns of A times row B. So you'd have your AB be AC times EF here. So kind of like the swap of that one. But for the purpose of this review, I'm going to be using a lot of this method. But either way, it's the same math, right? Same result. So quickly, reviewing the multiplying and following matrices, we're going to do this for an example. So quickly, I don't think the red, actually, does that show up pretty good? That's not bad, the red. So multiplying this matrix, we want to find what C is. I'm not going to go through the entirety of it, but I'll go through when we get into a flow of like doing this math, right? So what we're going to do first, I'm going to quickly choose a color. So first off, we're going to take this first, it'll be the column. Is it row? Row? That is a row, duh. Sorry. So you have that, and you're going to have your first column of the second matrix. So you're going to multiply element by element, and you'll get your first element of this resultant matrix. One important note is that when it comes to multiplying matrices together, the only case where a result will come out is when you have your first matrix, the number of columns is equal to the number of rows in the second matrix, right? So if you have like a 3 by 3 matrix times by a 3 by 1, that matrix should work, right? What you're going to get out, and I think that I kind of like cancel those middle parts here, you're going to get a 3 by 1 matrix, okay? So if you see any kind of problem where you have hold on, you have a 3 by 2 multiplied by a 1 by 2, just know that is not possible, okay? All right, so back to this. So we want to see what happens when we multiply these 3 by 3s together. We see that, of course, that's going to result in a valid answer because it's a 3 by 3. Number of rows, number of columns match the number of rows. So let's grab green here. So we're going to have 3, this first little portion here, times by -1, plus it'll be the second row element and second column element. So it'll be 0 times 7 plus 5 times 1. And that's just going to equal, it's going to be -3 plus 0 plus 5, which is equal to 2. Okay? So that's the first element in our matrix here. I'm going to denote this big green one as our matrix here. So this first element is going to be 2. Okay. Now, if we move on here, we're going to have, we want to look at the second element in this portion. We're going to look at the same first row, but look at the second column of the second matrix. So now we're going to change up some of our values here, if you don't mind. We're going to keep the same row elements, but I'm going to change the column elements. So we're going to have, instead of 3, we're going to have -1 times that -1 from this first element, right? Plus 0 times, and it's going to be 2 instead of 7. 2, and then you have 5 times the last element here, which is 8. So we're going to do times 8 instead. Now we're going to get -1 times -1 is just 1, plus 0 times 2 is 0, plus 5 times 8 is 40, which is going to result in 41. So that second element there is going to be 41. Like I mentioned, I'm not going to go through the entire matrix, but I'm just going to do one more example where we go down into the next row right here, okay? So instead of changing the column that we're going to be in on this side, we're going to now change the row we're going to be taking from the first matrix here. So I'm going to quickly just know we're going to be taking from this row. All right, so now we'll do the same thing, same math. So we're going to do, it's going to be 2 times -1. So it'll be 2 times -1, and it'll be -2 times 2. So we're going to choose a 0, be -2. It'll be 4 times 8. From this, we're going to get 2 times -1 is -2, plus 2 times -2 times 2 is going to be -4. It would be 4 times 8 is going to be 32. Add it all up together, we're going to get 26 here in this 2 element here in the matrix. Of course, you rinse and repeat for each element as you so please, but you'll notice that later on in the course you find easier ways to not just go through every single calculation, right, for this matrix. But are there any questions about that? About finding elements after multiplication? Great. This kind of goes through that same process where it goes through each element, but you'll notice we looked at 2, 41, and 26, right? That corresponds with the first element, first row. I guess first column, first row, second column, and then second row, second column. Okay. Wonderful. Yeah, that's what we get out of that. Do you feel like you would like to go through another example? Do you want to? If there's no need, I mean, that's the same. This is the same process here. So, okay. This goes through that as well in that example. So what kinds of matrices you encounter in linear algebra are these following ones. And we're going to go through each of these in their own way. We have the identity matrix where you have just ones across the diagonal. You have zeros everywhere else. You're going to have the inverse matrix, which describes the inverse operation of a matrix A. So you'll notice that when you multiply A by the inverse A, you're going to get the identity of that. Permutation is you have a matrix that swaps the rows of any given matrix, where you can, yeah, of course they permutates that. I think we'll go over that here in a little bit in this movie later. The singular matrix has the determinant where there's a determinant of 0. So that's an example of a singular matrix. Symmetric matrix is where the matrix A is the same as the transpose. You have your rotation, which causes some kind of rotation about theta in the given system. You have the orthogonal matrix, which is a similar, I guess, when you have A times the A transpose is going to be equal to the identity. And you have finally an elimination matrix, which used to eliminate a given entry or a given series of entries, which is exactly what we're going to go into right now. So we want to find an elimination matrix that eliminates the entry 3, 1. Yeah, sorry, go on. Yes. Yes, no, sorry, my apologies. I just wanted to speed run for some reason, so let me know when you're ready. So I think, do we not have access to like send these slides also, or?
I don't. For tonight.
I was gonna say I thought we did that a couple times where we could send them. Okay.
If not, this will be uploaded hopefully to the AMLAC YouTube. very soon.
Yes, that should be.
The Aggie Math Learning Center, because
EMRC is for engineers, Aggie Math Learning Center is for all the people on campus. And I work at the AMLAC and we're recording it and then we'll be able to.
Yes. Yeah, so either way, you'll have access to the slides. So, but if we're good, then we can go into the elimination matrix. So we want to find a matrix that eliminates the entry 3, 1 in this matrix. So really, we want to find something. We want to find some matrix that gets rid of this 8. We want to make that a 0. Okay. So quickly, I'm going to do something here with blue. So the way I like to kind of think about it is like you notice that throughout your linear algebra time that you've done row operations, right? Where kind of like you take, like you notice that you can multiply some row by some value and you can cancel other values in the matrix. So in this example, we're going to do exactly that. And that works because this system is linear, right? And if it were non-linear, that's kind of a problem. But since we're linear, this helps out a lot. So so one way I like to kind of think about tracking our progress and trying to find this matrix is we start off first off by the identity. So I'm gonna actually I don't know if I can do it quickly, but I'm just gonna write out this matrix 4, 6, 3, 3, 1, 2, and I'm gonna denote just some big line in here. I'm gonna put in the identity matrix. That's not it. That is definitely not the identity. But identity, all it does is that when you multiply some matrix by that, you're going to get the original matrix out. That's all that does, right? And so here, the identity matrix is going to be big when it comes to making a matrix that will eliminate this 8 here. All right. So what we're going to do is we're going to do some manipulations here, or we're going to do some math here to eliminate this 8, and we'll do the same thing on this side. All right. This big bar just shows us, it's just like a good way for me to track what's happening. So notice here that the second row can get rid of this 8 really easily with this -2. So we're going to multiply this second row by 4, and we're going to add it to the third row. So when I like to denote it, we're going to do, so R3, and I'm doing N for new, like our new row 3, is going to be the old R3. I'm going to make that a little smaller O, so it's old, not O. Plus 4 times R2. Okay. So now we're going to multiply this top row by 4 and add it to here. So you'll notice that this 8 will go away. That'll be a 0. 4 times 6 plus this new element 3. So 24 plus 3 is going to be 27. And you have the second row times 4. That's going to be 4 plus 2 is going to be 6. That makes sense where I got that. Any questions? Okay. So now we've done that with this side of the matrix. Let's do it on this side. So really the only thing that changes is going to be this middle element here because the other elements we have are 0, right? So 4 times this plus 0 is going to be 4. So this matrix here, this whole matrix is going to be the elimination matrix that gets rid of that element in 3, 1. So you'll see that here. Yeah, we get this nearly identity matrix with just this 4 at the bottom. All right? Okay. Let's do one more example. So I want to find an elimination matrix that will put the given matrix in upper right triangular form. So what that looks like in upper right triangular form, we're going to have some matrix. In this case, oh, that's blue. Hold on. Let's make it a little bit nicer to see. So we're going to have some vector that has some elements over here. We don't really care what they are, but we want to make these elements zeros. All right. So it's just an extension of the last problem, but now we're just going to eliminate a few more elements. So let's do that. All right, so now I'm going to set up the same way as I did with the last problem. 2, 1, 3, 4, 3, 7, -2, 0, -1. Actually, hold on. I got to have my big bar. Okay, wonderful. All right, so let's start with this element right here and try to get rid of this 3. So this 3, it can get a little tough to kind of see what would help out with eliminating that element, but we can do this. So we're going to use, I believe it's going to be, actually, let's get rid of this one. Wait, no. I promise I know what I'm doing. We're going to get rid of this bottom element with this second row element, okay? So we're going to do this. We're going to do, if we look at this, we're going to take 3 times this and basically subtract it from this. Or we're going to multiply this by -3 and add it to this row. So we're going to take, so R3 new is going to be equal to -3 times by R2 plus R3 old. All right. So we're going to have this times -3. Add it to here. That'll make that 0. I'm going to have this times -3 added to here. -3 times 3 is going to be -9 plus 7 is going to be -2. And then this element, of course, times by that and add it to here. That's not going to change. It is 0. So we'll keep that there. Now, that wasn't right, was it? Do we go to the second row first? That's fine. Okay. Yeah, we could do that. So we just swap these 2 rows. Let's do that. So we'll do. Of course, this will change, but I'm just gonna keep the same identity just for now. Oh yeah, duh. So we have instead, so we're swapping these 2 rows, right? So now instead, the identity is gonna look like this. Not like that, right?
Don't forget to get 3 to the
Yes, it did. Yes. So we have this row 2, adding onto row 3. So we're going to have this element be our -3. Follow so far? Okay. So now we're going to have this top row. We're going to cancel with this bottom row right here. And we're going to have, it's going to be a -2 times this top row added to the second row. Okay. So we're going to have R2 new, so equal to -2 times by R1 plus R2 old. So we're going to have this go to 0. This times -2 is going to be -6 plus 4 is going to be -2. And we'll keep this the same since 0 plus that doesn't really do anything. So, all right. And then if we apply this to this identity matrix here, we're going to have R2n is going to be R21 times by -2 plus onto the old one. So this will now be -2 here. Is that following right so far? Okay, I figured. So now we have this last element we want to take care of right here. So all we got to do now is we're going to have a new R3. And what we're going to do here, we're going to be multiplying this by -1 and add it onto the row 3 old. So let's do -1 times by R2 plus R3 old. So now we're going to have this times by -1 be a 2. 2 minus 2 is going to be 0. And then -2 will be times by -1 is going to be 2. Minus 1 is going to be 1. Now we're going to have the same operation here, where we have -1 times multiply here, add onto here. This will become a -1 in this element. And this will become a negative, this will be -2 times -1 will be 2 plus -3 will be a -1 here. All right. So you'll see though, also, I mean, you'll see that we have achieved this triangular kind of form. We don't really care about how this part looks, but rather that we have this form made. Any questions how I got there? Yeah.
You can swap rows, but you can't swap columns.
Correct. Yes, you cannot, because the rows, they kind of represent like an equation itself, right? And so, yeah, no, good question. Very good question. Thank you.
By one row by another. You have to.
Great question.
divide them by integer.
Yes.
Yeah, you have to divide them by.
Yeah, you can scale it. Yeah. however is needed. So
Oh,
yes, no, good question. So
say that you might can't divide, well, you can multiply by, like, say instead of dividing by 2, you could just say I multiply this row by 1/2.
Yeah.
Because that's closed under multiplication and division, right?
yeah, no, I mean, so long as you scale your row by either by dividing by 2 or by multiplying by 1/2, I mean, it's going to do the same operation. Same operation. Yeah. So when you think about dividing, I tend to think about multiplying by 1/2, but dividing, I understand the same principle. So
The actual closed under, I guess it's more closed under multiplication than it's like closed under division. Even though technically they're the same thing.
yes.
Um,
Do you know the question? The answer to that, I mean,
Really, multiplication and division are just the same thing.
just one is like inverse.
One is just the inverse of the other. Now, with that being said, you can't divide matrices by each other,
Mhm.
multiply them. So like, when it comes to linear algebra, division is the only way. There's no matrix division operation. Yes. But for scalar numbers, those numbers by themselves, then you have division, that's the same.
because like in a way, like when Carson mentioned, like it's kind of like an inverse. So you have the inverse matrix, which is big quotation marks. It's not division, but like that gives you the identity, right? And so really, we just deal with multiplication, even if we can think of it as division. So, right.
Well, and just.
You can do that.
Technically, there's no subtraction because it's just adding a negative number.
it's community.
Yeah.
Right.
You can't multiply one row by another as well, just like you can't take one row and divide it by another row. You have to.
Yeah.
Yes, you can.
No.
Yes.
So like in this example, we couldn't take the row 2, 4, -2 and divide it by 1, 3, 0. Nor could we multiply it.
Mhm.
That's not a linear.
You have to either do scalar multiplication or scalar division.
Right.
Change the matrix.
And that's because that would be a linear combination.
Yes. Yeah. Okay. Does that help a little bit?
Yeah.
Yeah. Okay, sweet. No, absolutely. No, they're good questions. They're very good questions because I know when it comes to these, I get so turned around too. So, but awesome, sweet. So you'll notice we got the same operations and whatnot. And we arrived to a point where it had the same matrix here. You'll notice quickly, actually.
Can I also ask, like, so if you go back one slide, this operation you didn't with that, and then you don't, right? We're just doing reduce row echelon.
Almost. So what's happening here? This is almost like a form of reduced row echelon. The reduced row echelon is when we have ones all across that, right? So, but like you said, this is going to be when we want to put the matrix in the right triangular form. This really is more so just to practice like eliminating certain entries in a matrix. But we will get to, reduced row echelon and all that stuff in a second here. Right, yeah. So, but wonderful. So notice this one looks slightly different, but if we just scale this matrix by a scalar value, then we actually get the same thing. So, with that being said, we're going to go on the form spaces here.
All right, so now we're going to talk about the 4 vector subspaces. So the first one is the column space. And what the column space represents is it's all linear combinations of the columns of A. And it's found by identifying what we call the pivot columns. And essentially, let's see, it doesn't include this, but if there is a solution to a matrix problem, so let's say we have some matrix A, I don't like that blue. If we have a matrix A and we multiply it by a vector X and we get a vector B, in order for that to be true, B must be in the column space of A. So if you have a solution to this problem, then B is in the column space of A.
You're saying,
Yeah, so
like, A is B has to be a 3 by 1.
for example, let's say we just have like the matrix. What's a good? Let's try and think of one.
The columns
They
have
want
the same dimension.
Is that? Let's do this.
So you have, say you have like a vector, like, say you have the
Huh?
vector 0, 1.
Yes, but I'm showing one that it's not.
That's, they make up a plane, right? So for that solution to be in that plane, it has to be some linear combination of those two vectors.
So look for this example I created right here. I created the matrix 1, 2, 2, 4, which as you can see, like the second row is 2 times the first row, or like the second column is 2 times the first column. So that means the column space of this matrix is just any scalar multiple of the vector 1, 2. Yes. So, but where we only have one vector, it making up our column space, there's not really any addition of other vectors. So it's just going to be a scalar multiple. So for a solution to exist to this problem, for an x and y, it must mean that this b vector exists as a multiple of the vector 1, 2. So in this case, this problem does not have a solution because 4, 5, the vector 4, 5 is not a scalar multiple of the vector 1, 2. Yes, if the vector was, for example, 4, 8, then there would be a solution x or y.
Scalar integer. Multiplied by an integer.
It depends on the size of your column space. So if your column space is just one vector, then it has to be a scalar multiple of it. But let's say we had a column space of 2 vectors.
I guess I'm asking.
Yeah. Yes, yes, yes. It could be. So for example, we could over here, if we had 1/2 1, that would also be a solution. That would also have a solution. Yes. 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 That's the lie along the line 1, 2.
Just another scalar.
Yes. Yes. Does that make sense?
I'm reading it.
Okay. Okay, cool. And we'll do a practice of finding what our column space is so we'd know what our vectors must be scalar multiples or linear combinations of. All right, the second is the null space, which is all vectors x such that a times x equals 0. And it's found using the free variables from reduced row echelon form. So similarly, how our column space included any b for which ax equals b, our null space includes any x for which ax equals 0. Then we have our row space, which is essentially the column space, but for our transpose matrix. So it's say that again? No, it does not. A doesn't even have to be a square matrix for you to find these subspaces. And we'll see that in our example too. So for row space, it's again very similar to our column space, except instead of AX, it's A transpose X equals B. So any B that solves A transpose times X must be in our row space. And finally, we have the left null space, which is very similar to our regular null space, except it's our A transpose. So if we have A transpose times Y equals 0, any Y that makes that possible is in our left null space. Any questions about the definitions of them? Cool? Okay. So we want to find the 4 fundamental spaces of this matrix. What the heck? Okay. Anyways, so when we want to do this, the very first thing we're going to want to do is we're going to want to put this in reduced row echelon form. And what that means is we want to get our diagonals to be 1 wherever possible. And we want to do that by doing elimination matrices, row swapping, etc. And we want zeros above and below those pivot locations. So when we do this problem, the first thing we identify is that we want this position to be a 1. It's already a 1, good job. So then we want to make sure that it's zeros above and below it. There's nothing above it, so we don't have to worry about that. Below it, we have a 0 and a 1. So that 0 is fine, but we need to adjust that 1. So just like how Ben did it, I am going to do a row operation. So I am going to do our new row 3 is equal to minus 1 times our row 1 plus our old row 3. And when we do that, our first row doesn't change. Our second row doesn't change. But our third row now changes. So we do 1 times negative 1 plus 1, that's 0. 3 times negative 1 plus 3 is a 0. 0 times negative 1 plus 1 is a 1. And 2 times negative 1 plus 6 is a 4. Now we look at the second column. And if we were to try anything to get this second row, second column to be a 1 value, we would end up messing the work we just did by making sure that that was a 0. So since it's impossible to do that, this is automatically a free variable column. So we're just going to now skip on to the next column, but in the same row. So we're now going to focus on making this value a 1. And it's already 1, so we're good. But we need to make sure above and below it are zeros. Above it is a 0, so we're good there. But we need to turn this 1 below it into a 0. And so we're going to do that by saying our new row 3 is equal to minus 1 our row 2 plus our old row 3. And in doing so, our first row doesn't change. Our second row doesn't change. Our third row has 0, 0 already. We have 1 times negative 1 plus 1 is 0. And 4 times negative 1 plus 4 is 0. So then at this point, we would move on and we would look at our next and final position and try to turn that into 1. But we can't do that without messing up the work we just did. So that is also going to be a free variable position. And now we look at the positions that we succeeded in making look like the identity matrix of 1s and 0s, and we call those pivots. So this matrix has 2 pivot columns and 2 free variables. So now when we determine our column space, we say our column space is the span of the vectors from the original matrix that are in the same position as our pivot variables. So we're going to look back at the first column and the third column from our original matrix, and we're going to say those are our columns. Does that make sense? Okay. So let's see. A span is the set of vectors that make up the space you're talking about. Yes. So for example, our column space, because we have 2 vectors, it makes a plane. Our column space is a plane in space. And these are the 2 basis vectors that make up that plane. Does that make sense? So we found them by determining through reduced row echelon form what our pivots were. And then I took the first column and I looked at the first column in our A matrix. And I just grabbed that directly and put it right there. And then I looked at our third pivot column, or our second pivot column, third column overall, looked at the matrix, the third column in our original matrix, and directly took it and placed it there.
Not a larger numbers than 1 and 0.
Yeah, it doesn't matter. Yeah, yeah. Mm-hmm. Yep. Yes.
What does it mean exactly to have like, I guess our free vectors, that just means that they can be like anything, because we're basically saying we have our original 3 row by 4 column matrix, right?
Mm-hmm.
And then we're saying that 2 of those vectors are actually redundant because they can be made by
The other 2. Yep. Yes. Yes.
it's,
Because yes, because those vectors are not linearly independent within the matrix. So that means they're dependent on the other vectors in the matrix.
And that's just by virtue of the fact that it's in the 2D
Yes.
space, right? Like
Yes.
the 2D space can be made up of 0, 1,
Um,
or 1, 0, 0. Any point can be reached using a linear combination.
Yes, that is true. Yes.
Like a physical standpoint for those two, if there was like A, B, C, D, that was each column, you can set B and D to be whatever you want.
Yes.
So for like, you could make it 0.
And we're going to see that in just a second when we find our null space. Okay. Okay. Sounds good. And if you run into questions, just let me know. Yep.
And it's always going to be the whatever columns correspond to your pivot column.
Yes.
It's always that way.
Yes.
You can have greater than or less than what you listed here. We could have
Yes.
independent vectors, or we can have, or at least one.
Mhm.
Good call.
Yep.
Okay.
Cool.
Yep.
All right.
Why?
Yes, so you are limited by the size of your matrix. So for example, if you have 4 columns in your matrix, the most your column space could ever be could be 4. Yeah.
The scales.
Yeah.
Why list your column space as the span of those 2 vectors when you could just say your column space is the span of the 2D vectors? Why do we have to put it as those 3? I mean, couldn't you say that the column space is
because technically there's infinitely many answers to this. So long as you have 2 linearly independent columns that are in the column space of this matrix, you can make up the span in any way. Usually how the LinDiff professors do it is because there could be infinitely many answers. They kind of establish this as the protocol for how you find the specific answers they're looking for.
they just make a plane, right?
Yes.
So really, we are saying that it's 0, 1, or it's 1, 0, 0, 1, but
Yes, but we're also looking at a plane in 3D space because they are 3-dimensional vectors. Yes, yes, you would. You would. Because this is again, a 3D, these are 3D vectors. So these don't exactly, these essentially, I think the plane that this is describing is is the XY plane lifted 1 off the Z axis, maybe?
so it would be true that it covers the span of, you could say that the span of 1, 0, 0, 1 lies in that, but then it doesn't describe that translation
Mhm.
words.
Yeah, yeah. Cool. Any more questions before we move on to finding our null space? All right, cool. Let me Erase these arrows real quick. All right, so we found our pivot columns and we found our free variables. So now we want to find the vectors of our null space. And first off, the number of free variables tells us how many vectors we're going to have for our null space. So because we have 2 free variables, that means we're going to have 2 vectors for our null space. So I'm going to set up a matrix in order to find those. And so we're going to have just 2 vectors, each with 4 values in it. And then we want whatever those are to essentially turn out into just zeros. Because that's what defines a null space. Does that make sense? Sorry? Yes, yeah. We're just finding what columns here and here would result in this matrix. So this is what we want to do is we want to use our free variables positions and we want to just set them to be any value. And in doing so, we'll be able to find our null space. And so usually the easiest way to do that is to let, for one of your columns, your one free variable at a time be 1 and the others be 0. So in this case, our first column, we're going to let our second be 1 and our fourth be 0. And for the other one, we're going to let our second one be 0 and our fourth be 1. Does that make sense? So because we have free variables here, we can choose any values to place there. Because they're free, they're not restricted. So we can choose anything. So we want to choose just the simplest values we can. So we choose the value 1 and 0. And so for the first vector, we place 1 to correspond to the second column, and 0 to correspond for the fourth column. And then we switch them for the second null space vector. Yes, so that they're independent of each other. Does that kind of make sense? Okay, then from there, we just need to figure out what these other positions would need to be. So for this first column here, if we multiply this matrix by the vector A1, B0, what we would get is we would get 1 times A plus 3 times 1 plus 0 times B plus 2 times 0. So we just get A plus 3. When we do our second row times that first column, we get 0 times A, 0 times 1, 1 times B, plus 4 times 0. And then it doesn't matter with this third, because we're just going to end up with a 0 no matter what we multiply it by. So what must A be in order for this to be 0? -3. And what must B equal for that to be 0? Sorry? So when we multiply this second row by this first column, we get B. So B has to be 0. So now we found our first null space vector. Any questions about that process? And now if we multiply this, we get 0, 0, 0. Now we want to do the same thing over here for our second column. So we have C0, D1 as our vector, and we want to solve for C and D. So when we multiply our first row by our second column, we get 1 times C plus 3 times 0 plus 0 times D plus 2 times 1. And that's equal to 0, so what must C equal? -2. Then we do 0 times -2 is 0, plus 0 times 0 is 0, plus 1 times D is D, plus 4 times 1 is 4. And we want that to equal 0. So what must D equal? Negative 4. And so now, once we've found our two null space vectors, we can write it just like we did with our column space. So we say the null space is equal to the span of the two vectors, and we just take these two columns, minus 3, 1, 0, 0, and minus 2, 0, minus 4, 1. Any questions about that? Yes.
So. You can find null space and write it like that.
Mm-hmm.
We've also, like, one way that we've been like taught to do it is like you can get your identity with your 1, 0.
Yes.
Side and take like the negative of your free variable.
Yes. Yes.
I know. Other way, you end up with a span of like two 3-dimensional vectors instead of two 4-dimensional vectors.
You should always end up with two 4-dimensional vectors for this case, because I know which case you're talking about, and that's, let's say we get a matrix, and after reduced row echelon form, we have it as like 0, 1, 0, 0, 1, and we have some A, B, C, D, 0, 0, 0, 0, right? And what you do is you take this free variable matrix, you multiply it by -1, and then you put it on top of the associated identity. In this case, since it's a 2 by 2, our associated identity would be a 2 by 2.
Yeah.
Why doesn't it apply?
It doesn't apply in this specific example because we weren't, that you can only use that when your pivot variables are right next to each other going from left to right. In this specific problem, because we have a free variable column right here that we couldn't change, you can't use that method directly like that.
Got to this point so that your identity was on the left and your free variables were on the right.
You can't do that because you can't swap columns. Yeah, yes. So the method I showed for this problem is the general method for any type of matrix. This method is only useful when you have the pivots right next to each other like this, and then the free variables afterwards.
So there's operation we could do that. The one on the left, it would just have to be like the one on the right.
Mm-hmm.
Okay.
But you can see there's a similar pattern that emerges because we have our free variables in these specific locations. What looks like our identity matrix is just split up in those locations. And the other parts are as if we had taken this and multiplied them by -1. So you can still do almost the exact same thing. It's just slightly different, and they're not going to be in the same positions. Exactly. Exactly. Does that make sense? Okay. Okay.
You have vector, like you're given a matrix that has like 11 vectors like the one we have right here.
Mm-hmm.
That means that it's gonna like simplify and it's gonna like crush it down to like a lower dimension, right?
Could you rephrase what you mean by that?
It'll collapse down like 3-dimensional vectors into like a 2D space.
Your dimensions, the dimensions of the space you're in never change. But the dimension of your actual vector subspace is dependent on how many pivots or free variables you have.
But if you have, say, like a 3x3,
Mm-hmm.
and you get a row of zeros on the bottom, meaning that you have, it collapses it down to more of like a 2-dimensional thing, right?
I wouldn't say that changes the actual dimensions of the problem at all. It just means you have a free variable.
Vectors are in a 2D space, right?
If you had
Dotted line on 3D space.
They
in the same
collapse.
plane, but that doesn't mean it's not.
so you're saying for an example like this where we do reduce row echelon form and it looks like this, right? All that means is you have one free variable and two pivots. And what that means is your column space is going to be two-dimensional in a 3D space. And your null space is going to be one-dimensional in a 3D space. So it only changes. Yes. Yes. The space they're in doesn't change, but the space of this vector subspace itself changes. If that makes sense. Um,
That's a very general.
yeah, I can't comment on that, I don't think. All right. Any other questions?
How we think of it, algebra, it's just like, just a different way of thinking about it sometimes.
Yeah, one thing that is kind of good to know and a good kind of mental check when you're doing this is the dimension your column space vectors are in always matches the number of rows you have. Or yeah, number of rows you have. Meanwhile, the size of your null space vectors always matches the number of columns you have. So in this problem, we have 3 rows. 1, 2, 3. So all our column space vectors are 3-dimensional vectors. Meanwhile, we have 4 columns. So our null space always has 4 dimensions in their vectors. So that's a good mental check as you're solving these as well, is once you have your column space or your null space vectors, you can check to see that you have the right number of rows in your vectors. Mm-hmm.
Always gonna have it in.
Yep. Yep. Yes. So the size of the vectors are always going to match those. But as you can see here, yeah, our null space and our column space are 2D, two-dimensional, because we only have 2 vectors for each of them. Yeah.
2 by 2, like say like 1, 0, 0, 1, and we have a trivial null space.
Yes. So in that case, if you had like a 2 by 2 and you did reduced row echelon form, and after reduced row echelon form, you end up with the identity matrix, that means that your column space would be just those identity vectors or whatever vectors came from your original matrix, and your null space would just be the trivial 0, 0 vector. That is,
Zero, but
yep,
if you have 3 vectors, then you can have a linear combination.
yes, yes. So again, your number of free variables tells you how many vectors you're going to have in your null space. So if you have 0 free variables, you have a 0-dimensional null space. If you have 1 free variable, you have a 1-dimensional null space, 2 free variables, 2-dimensional null space, so on and so on.
So that means, even though you have redundant vectors in your matrix, right? Even though you have, like, the matrix we have 2 vectors, and then we have 2 pivots and 2 free
Yes.
vectors, right? For free variables.
Mm-hmm.
That just signifies that they're like carrying information that we're in, like, whatever space that.
Yes.
Okay. And that's what allows us to find the null space of that even though it's a plane in that space, there's a linear combination of vectors from the information in that space that allows us to push it to zero. Is that kind of what we're saying, or?
I think I got kind of a little bit lost there at the end.
Space.
Okay.
I mean, have two vectors that, so you have two pivots and one free.
Okay. Mm-hmm.
So you have a plane. Vector, or span of vectors. And then you can take a linear combination of that last vector and push it to zero, right? But I'm kind of curious about like how it carries, like, does it just carry information? Is that why it's important?
Yeah, it's essentially the free variables are because they're dependent columns. It's just kind of additional information that you don't need to get to the actual answer of the problem, if that makes sense. Really, your null space and your column space don't necessarily exist in the same dimension of space. Like in this example, our column space exists in 3D, but our null space exists in 4D, so they don't exist in the same dimensional space. It just means that the null and column space kind of correspond to different locations and different things you're trying to solve. So the next two vector subspaces are companions to these. So the row space and the null space do always exist in the same dimension of space. And your column space and your left null space always exist in the same dimension of space. So those are really the companions to each other. Is we tend to group up the column space and the null space because they're both dealt with A and not A transpose. But it's really the column space and your left null space that are partners, and your row space and your null space that are partners, and help you solve their problems together.
So if you have two-dimensional column space and a three-dimensional null space, what does that really like tell us about the vector or about like the space that we're working in?
So are you saying the column space is two-dimensional or the column space exists in 2 dimensions?
Like, example,
Okay.
column space that ends up being the span of what, 1, 0, 0, 1.
So this is when you have a square matrix, that is the situation where they will always exist in the same space. Because like we said, our column space always matches the always exists in the space of the number of rows, and our null space always exists in the dimension of your columns. So when you have a square matrix, you have the same rows and columns, so they will exist in the same exterior space. Make sense? Okay. Any other questions about those two? All right. No, I like this. You guys are asking like really, really good questions. I know when I took LinDiff, this section was probably the most confusing to me. It's very conceptually difficult. So I'm happy you guys are asking questions about it. All right. Now, how we find our row space and our left null space. So we already have the tools to find our row space. Normally, how it's done is once you've put your matrix in reduced row echelon form, the same pivots that you have, you take those corresponding rows instead of columns. So all we're going to do, let me erase this real quick, is we're just going to take those first 2 rows from our reduced row echelon form, and that is the span of our row space. Yes. So it's going to be 1, 3, 0, 2, and 0, 0, 1, 4. And we transpose them to make them column vectors. Does that make sense? Any questions about that? All right. So now we want to find our last one, which is our left null space. And unfortunately, that is the only one where we don't get the information we need from our reduced row echelon form of the normal matrix. What we're going to want to do is we're going to want to transpose our original matrix and then perform a reduced row echelon form again. So when we take the transpose of A, we get the matrix 1, 3, 0, 2, 0, 0, 1, 4, and 1, 3, 1, 6. And now we're just going to perform reduced row echelon form. And let's see if I can do this quickly. We leave that the same. That gets fully eliminated. We get rid of that. That stays the same. And that goes down to 4. We can swap these two rows. And we will be left with 1, 0, 1, 0, 1, 1, 0, 0, 0. So I just did that quick because that's the same type of elimination stuff we did earlier and that Ben went over. Does everyone follow that? We're going to take columns. So once again, we're going to identify our pivots and free variables. So we have pivots in the first two columns and a free variable in the third column. And this one, we have it in the block matrix form with that identity. So we can use that method we talked about earlier. We can just take this column, the free variables above the 0, and we can multiply it by -1. And stick it on top of the associated identity matrix. Since we only have one vector, that associated identity is just going to be a scalar value of 1. So we stick it on top of 1, and that is the sole vector that makes up our left null space. Any questions about how I got that? Mm-hmm. Yep. 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 And we can check it if we multiplied this matrix right here by the vector -1, -1, 1, we'd get 0 out. Cool? And then again, as you can see, like I was mentioning earlier, our column space and our left null space exist in the same dimension. They both consist of 3-dimensional vectors. Then our null space and our column space both exist in 4-dimensional space because they're 4D vectors. That will always be true. And you can also tell our column space is equal to our number of pivots, and our null space is equal to our number of free variables. And those, the amount of vectors we have between those add up to our total number of columns. So we have 2 column space vectors, 2 null space vectors, which adds up to 4, and we have 4 columns in our matrix. Similarly, our left null space and our row space, we have 2 vectors in our row space and 1 vector in our left null space, and those add up to 3, which is the number of rows we have, which is another mental check to make sure you did everything right. So here's a good, the dimension of our column space plus the dimension of our null space equals our number of columns, and the dimension of our row space plus the dimension of our left null space equals the number of rows. Yep.
Where you have C written, you make it a little bit more C shaped, just so it doesn't.
Yeah.
There you go. Thank you.
Let me change this one too. There you go. Does that help? Okay, good. I'm glad. No, yes, I do notice that problem sometimes when I do my homework, so. Yeah. Oh, yes, yes. Cool, I'm glad. All right. Any other questions about our 4-vector subspaces? Feeling better about these? All right, cool. And yes.
They have a square matrix
Okay.
that like is the case for these.
Mm.
They're all same.
So if you have a square matrix just in general, they will all exist within the same dimension of space. But they still might, each vector subspace might have varying dimensions, if that makes sense. So you could still have a 2D column space and a 1D null space, but both of them reside in 3D space. Cool. Yes, yes. All right. And then here's the process we just went through. And then I had another one for practice, but for time, we're going to go ahead and move on to the determinant.
Okay, so now we're gonna take a look at the determinant as kind of a throwback to like kind of matrix mathy stuff we were doing earlier. It's kind of just a bit more computational. But we use it a lot kind of in like bigger picture processes, right? It's normally a step that we have to pause and compute. But there are some properties of the determinant that are good to know. First is that the determinant of the identity matrix is always going to be 1, right? Which checks out when we get to work through the computation part of it. And then also, every time we swap the rows of a matrix, that will switch the sign of the determinant. So the value will stay the same, but the sign will swap with every row swap. Does that make sense? So if we do 2 row swaps in our matrix, then our determinant will come out back positive, right? So just every time, it just flip-flops. And then we can also factor out constants or scalars out. If we factor out of the matrix, that will be scaled out of the determinant as well. All right. Oh, I guess I'll use this. And then this is just the procedure of taking the determinant of a 2 by 2, right? We multiply A and D, and we subtract B and C. And then we get to extend that into the 3-dimensional version where we have the determinant of the every of the columns that exclude the column of interest at the top, and we take smaller determinants of these 2 by 2s. And then so we have some examples for each of these, and then depending on how comfortable we are with them is how fast we can move through them. So just real quick, it's kind of conceptual. If we have this matrix with a row AB and a row 0C, then what, and its determinant is 2, then what would be the determinant of the matrix where we have row AB on the bottom and row 0C on the top? Right, -2. So it's just every time we swap the sign as well. And then kind of another quick conceptual is if we have this matrix where we have these 5 scaled in here and the determinant is 100, what would be the determinant where those 5s are taken out? So it's it would be 20, right, divided by 5, because we divided the A and the I by 5, right? So it's the same procedure on that. So that'd be 20, right? And it's kind of easier to think about this one in the reverse. Like if I scaled this right-hand matrix by 5, right, multiplied it by 5, then I would get 100. Yeah, it's kind of like better, easier in the reverse. Exactly, right. Multiply by 1/5. Okay, and then we can walk through a practice of taking the determinant of a 3 by 3. Do you guys want to do this, or do you feel pretty good about this process? Good? Okay, awesome. Okay, and then we're going to talk about eigenvalues and eigenvectors, right? We utilize these a lot in a few different applications, right? Diagonalization, solving systems of differential equations, right? So these apply to a couple different larger scale problems. Let's the rotation matrices. Um, I believe. I believe the rotation matrix uses more transformations than eigenvalues and eigenvectors. Does that check out? Okay. Yeah. So we are able to derive how we get our eigenvalues and eigenvectors from this initial equation up here, which basically states in words that the matrix A multiplied by a vector x equals the scalar multiplied by that same vector x. So we use this to find our eigenvalues and eigenvectors by subtracting this oh my gosh, sorry guys. This right-hand side over to the left-hand side. And then because we subtract this lambda value over, we need to turn that into a matrix that has the same dimensions as A, so we just multiply it by the identity. Then we can factor out the x vector. And then in order to achieve a non-trivial solution for that x vector, which is our eigenvector, the determinant of the inside parentheses, A minus the eigenvectors, right, equals 0. And we utilize that to solve for our eigenvalues. Okay, so this would just be a quick walkthrough of how we solve for the eigenvalues, utilizing that the determinant of A minus the identity matrix multiplied by our eigenvalue is 0. So we start by implementing that A, which is 5. When we subtract the eigenvalues along that identity, we just get that along the diagonals, right? Keep that, and we have a 6. And then again, subtracting along the diagonals. And then we know the determinant has to equal 0. So we're going to take the determinant of this 2 by 2. So we take the determinant, right? We get to multiply, kind of do that cross multiply, where we have -5 times lambda multiplied by 2 minus lambda minus -12, which is plus 12. And then we get lambda squared plus 3 lambda plus 2. And then from there we can factor our lambdas, and then we get lambda plus 1 and lambda plus 2 will create that polynomial. Therefore, our eigenvalues are -2 and -1. So the plus 12 is when I break this down, we get a positive 10, -10, and then a plus 2. So I kind of skipped some of the algebra, but yeah. No, yeah, you're totally good. Okay, so that would be our final answer for the eigenvalues of this matrix. And right, just a little quick answer check at the bottom there. Does that all check out? Awesome. And then from there, right, we get to find our eigenvectors, which we can calculate by plugging these eigenvalues we just found into our original equation, and we want to find what vectors x will make that equation 0. So we'll do our first one, lambda 1 equals -2. And I'm ordering these so that the magnitude of the values, the greater ones, are first, right? We kind of just want to go through decreasing. Yeah, mostly just magnitude, right? So if we had some positive ones in there, I would still just want the greatest magnitude to be first, just because that'll be helpful in some later problems or applications. Yeah, especially in diagonalization is where it really gets utilized. Yeah, all good. So we have our -5 plus our minus -2 gives us -3, and we get to keep our other values, and then minus -2 is 4. So then we want to find what eigenvector x1 and x2 are going to solve for 0, 0. And in this case, we can see that if x1 is 2 and x2 is 1, and we were to multiply that, it would solve for 0, 0 each time. So that's our first one. And then our second eigenvector, very similar procedure. Right, we have -5, subtract -1, -2 minus -1 is 3. And again, what eigenvector, when multiplied, will give us the result 0, 0. And in this case, our eigenvector associated with the second eigenvalue would be 3 and 2. And we can see if we multiply that, right, matrix multiplication, -3 times -4 would be 12, plus 6 times 2 would be 12. So that would equal 0 for both of those rows in the multiplication process. So does that kind of check out, right? We end up doing this same procedure a lot for several different problems, right? So it's just good to have the routine down. But it is very just like computational, right? Okay. For which part of the equation are we looking at? Right here? Mm-hmm.
Take that matrix on the left, that's -3, 6, -2, 4. You were to take its inverse and multiply it over to the right for that.
Yeah, we don't typically do that. Yeah. So the kind of more tried and true method would be what we're basically doing when we're like kind of checking these values is like a quick version of reduce row echelon to the identity, right? If you remember, doing that is another way to solve larger systems of equations more step by step. So it's kind of what we were doing here, just kind of like a zoomed ahead process because these numbers are kind of easier to work with. Does that, yeah, kind of check out? So yeah, so you could find the inverse and multiply. A lot of times it's not super helpful because like if you're given like a 3 by 3, it's not, yeah.
So you're gonna get a trivial space, or like a trivial.
Yeah, because we're solving for 0, right? So if it was any other numbers, then it could be helpful, but depending on the size of our matrix, it might not even be the easiest method either. So yeah, that's how I would approach it. Yeah. Okay. So then moving on to diagonalization is a great place where these eigenvalues and eigenvectors get utilized, right? So diagonalization basically breaks it down and says that a matrix A can be expressed by the multiplication of these 3 matrices where this V is the eigenvectors and then this capital lambda is the matrix of the eigenvalues that correspond to those eigenvectors in the matrix. And these are really useful in practice based on these other 2 things that we get from this, right? If we raise A to a power and we know the eigenvalues and eigenvectors, we can raise that lambda matrix to that same power and they are equal. And this really helps us to look at like long-term behavior of linear systems. And then additionally, I'm sure y'all have seen, right, where they are expressed as the sum of rank 1 matrices, which is useful as far as like, it's useful kind of in like data storage in matrices, right? Determining which matrix we want to keep, right? It's kind of where we like resolution comes from, is how many rank 1 matrices we include. Yeah, exactly. So that's a very good application of these things. Yeah, so the rank 1 matrix, we'll do an example with it as well. Would you prefer to use it with numbers or just the rank 1? Yeah, so the rank 1 in this case is going to be created from the multiplication. So if I have my lambda or my capital lambda matrix, and then I have like lambda 1, lambda 2, lambda 3. The rank 1 matrix will be the matrix that comes about from multiplying the corresponding, or like the rows and columns that will be multiplied by this lambda 1, whereas the rank 2 is associated with the lambda 2, and so on and so forth. So yeah, and then we'll be able to work it out in a little bit. Yeah. So, but yeah, they're associated with those eigenvalues as they're placed in that lambda matrix. Okay, so this is just utilizing finding our diagonalized matrix, or using diagonalization to find the original matrix as well. So in this example, we're given the eigenvalues and eigenvectors, so we don't have to calculate it each time, but we can create our matrices. So our eigenvector matrix, right? We have 3, 2, and 1, 1, our capital lambda, right? Again, these have to correspond with the vectors that we place. So because we had eigenvector 1 is 3, 2, the corresponding eigenvalue is 11. So just make sure we keep the order straight there. And then we can find the inverse of our eigenvector matrix, which thankfully, if we take the determinant of that, we have 3 minus 2, which is just 1, which makes it nice for us. 1 over 1. And then the determinant is right, we swap those A and D spots, and then -2, -1. And then from there, we can just multiply all these together according, like the formula states. 11, 0, 0, 3, 1, -1, -2, 3. And then from there, we just do the matrix multiplication to get our A matrix. Do you guys want to go through that, or do you feel like you understand the concepts behind it more? No, as long as they're right next to each other. So you could do these two first, or these two first. But yeah, so either way. Mm-hmm.
Like, I didn't really have any really good convention for which one would be one. Is there any good way to like say this is eigenvector 1?
Yeah, so when we look at say either the rank 1s, the rank 1 situation, right? Or even this like long-term behavior system, the convention of why we want to have like lambda 1 have the greatest magnitude is because a lot of times that will dominate either the information contained in the rank 1 matrices, or like if it's raised to infinity, right? Long-term behavior as t approaches infinity, the larger eigenvalue will dominate that behavior. So conventionally, it's just that's why we have greatest magnitude is lambda 1 and kind of decreasing, so on and forth. Yeah, right. Because it helps with both of these two applications, because as we break these down or raise them to infinite levels, right, the larger ones will dominate both of these cases, right? Data storage and yeah, sure. I mean, yeah. But yeah, so it's just helpful to see which will dominate FX as it moves forward. So yeah. And then this is kind of that rank 1 example. Thankfully, I already calculated the eigenvalues and eigenvectors, so we don't have to do all that computation. So it's a similar, same process as before, where we have our eigenvector matrix, our eigenvalue matrix, and then our inverse, which again, thankfully the determinant is 1. We have 21 minus 20. So we don't have to multiply that or work with fractions. We apply our position swaps and make these negative. And then I'm gonna write it all out to see what it looks like in the context of the original equation of the diagonalization. Okay, so because we're asked for the rank 1 matrix, right, my value of interest is going to be this lambda 1 position, or like this first pivot point in the first column. So basically, when we do our big matrix multiplication, we're basically saying we're looking only at this one, and this is not going to matter. So in that case, a lot of the matrix multiplication that we do, a lot of columns will become 0. So because 8 is just a scalar, basically, essentially, in this matrix now, we can just multiply this column and this row and scale it by 8. So that's what I'm going to do here, because the rest of that lambda matrix is 0 as well. So 8 is just going to scale at this point. Multiplied by 7, -4. And then we do our multiplication from there, where we get 21, -12, 35, -20 scaled by 8. And then in this question, yeah, it's just asking for the rank 1 matrix. So we'd multiply 8 into our matrix. And then if it was asking for our rank 2 matrix, we would be interested in the pivot point in our second column, this 4 here. And that would correspond to the second column and second row is what we would end up multiplying. So that's some different questions that are kind of associated with diagonalization, aside from just like the basic formula. So I think that is it for my stuff. Yeah. Exactly. Yeah. No?
That would also be a rank 1 matrix. We would just call it the rank 1 matrix associated with our second eigenvalue. Because the rank of a matrix is dependent on how many independent columns you have. So a rank 1 matrix has one independent column in the matrix. Yes. Yes. So we would call them like our first eigenvalues rank 1 matrix or our second eigenvalues rank 1 matrix, but they'd both be rank 1 matrices. Does that make sense? Okay, cool. Yeah, that's another term for just saying how many independent columns you have. So like back when we were doing our column space. Yes, yes. The number of pivots tells you what rank your matrix is.
So each capital R is a rank 1.
Yes.
And then this is just the associated.
Oh, like
Yes.
Yeah, so.
First.
Yes. Yes. That's exactly it.
And
Yes. Mm-hmm. Yep. All right. Now we're going to talk about how we use linear algebra to solve systems of differential equations. So first, we're going to want to find a null solution. And how we find the null solution is we create our companion matrix A, and then we find the eigenvalues, and we set it up in the form of the sum of e to our first eigenvalue power times our first eigenvector plus e to the power of our second eigenvalue times our second eigenvector, so on and so forth. Then, okay, I don't know why that appeared second. We'd set up our system into a matrix before doing that. But then you also want to find your particular solution. So you create what we call the fundamental matrix. You find the inverse of the fundamental matrix, and then you use this equation to find your particular solution. And we're going to run through a practice where we do all this. But any question just about null or particular or anything like that? Sounds good. All right, good. All right. So we're going to practice it with this system. X prime equals negative 10x plus 18y, and y prime equals negative 6x plus 11y. And I went ahead, and because we just went over eigenvalues and eigenvectors, I'm not going to go through that process, but those are what you get when you solve those. But I will go ahead, if we set this up as a companion matrix, we get x and y prime is equal to negative 10, 18, negative 6, 11 times x and y. But as we can see, we also have this plate plus 8 to the t, plus e to the t, I mean. So we're going to want to add that as our forcing function vector. Any questions about how I set up this system? Because up here on the top, we don't have any forcing term, so that's 0. But on the second one, we do have a forcing term. If you didn't have a forcing term, then these would just be 0. You wouldn't need to include it, and your solution would just be your null solution. Yes. Yes. Yep. So we have a forcing function in the y direction. All right. Any questions about how I set that up? Cool. Again, if you take this companion matrix right here and find its eigenvalues and eigenvectors, you'd find those. So we can go ahead and we can say that our null solution is equal to e. We raise it to the first eigenvalue power and multiply it by t. And then we multiply the whole thing by our first eigenvector. Then we add our second e. We raise it to the negative first power and multiply it by t. And multiply the whole thing by our second eigenvector. Any questions about that? Yep. Mm-hmm. Yep. Yep. All right. Now we want to find our particular solution. And we do that by setting up our fundamental matrix, capital Phi. I like to call it the big green lantern symbol. So we set up our big green lantern symbol and we set it equal to, and essentially all we do is we take these e's and we multiply them in. and then we combine them into a 2 by 2 matrix. So it's going to be 3e to the 2t and 2e to the 2t and 2e to the minus t and e to the minus t. Does everyone see how I set that up? Mm-hmm. Yep. All right. And if we remember, our equation for the particular solution was our green lantern times the integral of the inverse of our green lantern times our forcing function integrated over t from 0 to t. So we have our phi, we have our F matrix because it's right here. So the only component we need left is our phi inverse. And we're going to find the inverse just like we take the inverse of almost every matrix. So we're going to do 1 over the determinant. And the 1 over the determinant, we do our little fish. We have 3e to the 2t times e to the minus t. So we have 3e to the t minus 2e to the minus t times 2e to the 2t. So we get a 4e to the t. Then we swap the diagonal positions and multiply the off diagonals by -1. Now, this denominator of our determinant, we can combine those, and that's the same thing as a minus e to the minus t if we were to move it up. So we're just going to go ahead and we're going to multiply a minus e to the minus t into this matrix. So we get minus e to the minus 2t, 2e to the minus 2t, 2e to the t, and minus 3e to the t. And now we have our inverse phi, or inverse green lantern. Cool? Now we just plug our pieces in part into that equation up there. So we have our x sub p is equal to our fundamental matrix, 3e to the 2t, 2e to the minus t, 2e to the 2t, e to the minus t, multiplied by the integral from 0 to t of our inverse. So we have minus e to the minus 2t, 2e to the minus 2t, 2e to the t, and minus 3e to the t. And we multiply that by our forcing function, 0e to the t dt. Cool? All right, let me see if I can make some more space. Yes. Oh, nope, that is not. I'm trying to figure out if I can grab this at all. Oh, what did that do? No. I feel like this button should. No. I wanted to move this, but that's okay. I'll just rewrite it over here. All right, so when we want to go ahead and multiply those two together. So our fundamental matrix will carry down. That's a 2t. Keep our integral. But when we multiply this, we do minus e to the minus 2t times 0 and 2e to the minus 2t times e to the t. So we get a 2e to the minus t. And similarly, when we multiply the bottom row, we get a minus 3e to the 2t. So now we just need to integrate. This stays the same. I'm sure if you wanted to cut down on not rewriting it every time, you probably could. And when we integrate this, we integrate each component separately. So the top part, when we integrate 2e to the minus t, what do we get? Yep, we just get a minus 2e to the minus t. And how about when we integrate that bottom part? A minus 3/2 e to the 2t. Now we just multiply this matrix with this vector, and we will have our particular solution. So when we multiply the top, we get a minus 6 e to the t minus a 3 e to the t. So we end up with a minus 9 e to the t. And when we do the bottom part, we have a minus 4 e to the t minus 3/2 e to the t. And that comes out to a minus 11/2 e to the t. And that is our answer. Yep. And so then our general solution, I'll just go ahead and, oh, I gave myself 2 slides and I didn't use them. So our general or complete solution would have both pieces are null and are particular. And our null, we want to make sure we include that it's multiplied by c's out front. So we'd have c1 e to the 2t times 3, 2, plus c2 e to the minus t times 2, 1, plus, and then we'd have our vector we found, which was minus 9 and minus 11/2. And this would be our complete solution, which means x equals c1 c1 times 3e to the 2t plus 2, or c2 times 2e to the minus t minus 9e to the t, and y equals c1 times 2e to the 2t plus c2 times e to the minus t minus 11/2 e to the t. Any questions about that process? All right, very cool. That is the end of our topic today. If you want to give us any feedback, we'd really appreciate it. It would help these to go better in future semesters. Besides that, again, thank you for coming tonight.